Welcome to NERF SimCenter's Live Expert Tips. In this session, we will introduce you to computational fluid dynamics simulations and how to characterize the atmospheric boundary layer flow for using our wind engineering with uncertainty quantification tool, or WEUQ. Our expert today is Dr. Fei Ding. She is a postdoctoral researcher at UC Berkeley and lead developer of the WEUQ tool. She received her PhD from the University of Notre Dame in civil engineering. Her research interests include the assessment and mitigation of wind hazards on structures through digital design tools, including CFD-enabled aerodynamic shape tailoring of structures, and physical systems for morphing structural profiles under wind. Fei, thank you for being here. The floor is yours.
Thanks, Matt, for the introduction. And hello, everyone. Welcome to today's Live Expert Tips. So in today's presentation, I'm going to talk about in the computational wind engineering, how we can characterize the atmospheric boundary layer flows to generate the inflow turbulence in CFD modeling using the SimCenter application WEUQ. So this is the outline of today's presentation. First, I will give a brief introduction to the SimCenter and the SimCenter application WEUQ. And the next part, I will give a brief fundamental knowledge about how to set up the CFD model in open form. And so today's focus is on the third part. So we will talk about the inflow turbulence generation that can characterize the atmospheric boundary layer flow in CFD modeling. And at the end, I will give two demos. One is for the Antidomain analysis, and another one I will talk about the wind flow around tall buildings and using WEUQ to generate the inflow turbulence. So SimCenter has developed multiple applications to model the natural hazards. For example, the EUQ is for earthquake engineering, WEUQ is for the wind engineering, and HydroEUQ is for hydraulic engineering. And so these applications have such interface, so it's convenient for users to give their model parameters to run the simulations and provide an interactive computing environment. And so to use this SimCenter app, you can download from the SimCenter website, which is stored. This app are stored in the design safe. So for example, if you want to run a CFD simulation using WEUQ, you can download the WEUQ app from the SimCenter web. And so if you so we allow the simulations to be run either in your local computer or in your TACC HPC nodes. But for CFD simulations, normally we need at least 16 or 64 or even more 100 processors to run the simulation. So it's not feasible to run the simulations in your local computer. So in this case, you set up the model parameters in WEUQ, and through the interface, the job will be submitted to the TACC frontier to run the simulation. So after the simulation is done, and the results will be archived in this design safe data depot, you can directly access the data depot to download the data, or you can directly download the data through the WEUQ interface. And this is a WEUQ, and it integrates the QualFAM. This is an application for uncertainty quantification analysis, and also the wind loading analysis, and with the structural analysis using OpenSys to determine the structural responses under winds. So far, we have multiple features in WEUQ, and after you download the applications in the event module, you can select different features to run your the hazard analysis. And one is a stochastic wind. You can generate the stochastic wind speed through the user interface. And we also allow the database enabled design. So in the WEUQ, currently we include the Vortex wind database and the TPU Tokyo Polytech University low-res database in it. And you can use a button, choose your building geometries and wind directions simulations to generate the full spectrum of pressure distributions. So I will give a more detailed information in the next slide. And we also enable users to run the CFD simulations using the WEUQ, and also it incorporates the TInF. So TInF is a turbulence inflow generation application also developed by the SimCenter to allow the inflow generation to satisfy the prescribed atmospheric boundary layer characteristics. So this is a user interface for the WEUQ. And for the database-enabled design feature, as mentioned, we have two databases currently included in the WEUQ. Vortex 1 is developed by the NetHash lab at the University of Notre Dame. So in the Vortex 1, we use the DEDM HRP. This is an aerodynamic database for high-rise buildings. So in this database, you can select the building aspect ratio and the building side ratio. And you can select the terrain roughness category and your wind speed and incident wind directions. And after click the button, you can directly obtain the full spectrum like the along wind, crosswind, and torsional moment spectrum. And download the data from the website. And another one is a TPU database for isolated low-rise buildings. Also, you can select the aspect ratio, side ratio of the building, and you can select the roof type and roof pitch and incident wind directions to generate the pressure distributions on the building surfaces. So we also allow the users to run the CFD simulations in WEUQ, and the jobs will be directly submitted to the TACC from TACC HPC resources. And so we have two features to run the CFD simulations. So if you define yourself as a CFD beginner and you want to run your first CFD simulations, you can use a CFD basic, and you give the inputs parameters for your computational domain and your boundary conditions, and you have some the turbulence model and the solar numerics, and which can be you just follow the CFD guidelines online, and you click the button run and design save. The job will be directly submitted to the TACC from TACC. And once the simulation is done, you can download data from the get from design save. If you have a lot of experience in the CFD modeling, you can directly use the CFD experts. So you need to prepare for all the files that need to be run a code in OpenFOAM, and use a browse the button to upload your folder to the CFD expert and select your solver, and this interface will give you access to submit a job to the TACC from TACC nodes, and also you can download the data from the get from design save. So next part, I will talk about what kind of files are needed to run the CFD simulations, especially in OpenFOAM. This is an open source software to run the CFD simulations. So WEUQ is based on the OpenFOAM. So today I will talk about some like fundamental modeling in CFD in OpenFOAM. So the first step, you need to define your geometry of your structure. Like, for example, if you have a building and you need to select what kind of mesh generation tool you want to use. For example, block mesh, they generate a structure mesh in the computational domain. So if you use this function, you need to input your building geometries in your block mesh file to generate the whole topology of the mesh in the computational domain. The snappy hex mesh is easier compared to the block mesh. In the snappy hex mesh, you need to provide the building geometries in STL file. So the STL file can be generated through the CAD or SketchUp or other softwares. And you provide the STL file, and the snappy hex will generate the hex and also the split hex mesh in the computational domain. And you need to refine some local regions that is critical, for example, close to the building surface and or at the bottom of the computational domain to model the boundary layer flows. And so once the mesh generation is set up, and you need to determine the boundary conditions in the computational domain. And especially today's focus is on determining the inflow boundary conditions that satisfies the prescribed statistical properties like the wind speed spectrum and the coherence, spatial and temporal correlations. And once the boundary conditions are set up, you also need to determine what kind of model fidelities in CFD. So currently, the direct numerical simulation is not feasible for CFD simulations around the large-scale structures. So the runs, the Reynolds average Navier-Stokes, or the unsteady runs, and the large eddy simulation are the workhorse. So once you select the model fidelities, you need to determine the turbulence models in each model fidelity. For example, if you choose to use runs to simulate the wind flow around the structure, so in the runs, we have K epsilon or K omega turbulence models, and you need to select appropriate one. And you also need to select the numerical solvers to solve this finite volume method. So for example, pisoform is for the transient flow and incompressible flow, and the simple form is for the steady state and the incompressible flow. And you need to choose appropriate solver to solve this, the computational simulations. So after the simulation is done, you can use Parallel to visualize the flow domain to see how the wind flow passed through the building. Or you can use other post-processing tools like Python or MATLAB to plot the pressure distributions on the building surfaces or the time histories of force coefficients of the quantities you are interested in. And to model the CFD, the simulations in OpenFOAM, the learning curve is even steep because all the files in OpenFOAM are written in C++ code. So you need to create each files and put the files in their corresponding directory. For example, in the system directory, it contains your runtime control and the solver numerics. And in the constant directory, under your case directory, it contains your physical properties, or turbulence properties, and your mesh generation. And in the zero directory, it contains your boundary and initial conditions. And after all these files are prepared, you can run these commands either in your local computer if you have multiple processors, or you can submit this shell script to the frontier to run using their HPC resource. So now we will come to the characterizing the atmospheric boundary layer flows. This is important because in our built environment, most of structures are immersed in our atmospheric boundary layers. Due to the terrain roughness, we can visualize the gradient of the velocity and the turbulence intensities. So in CFD modeling, it's important to accurately model this gradient information on the inflow surface to provide appropriate scheme for the inflow turbulence generation. And besides accurately describing these statistical informations on the inflow surface, another issue is how can we generate the time series of inflow turbulence velocities based on this prescribed information that characterize the atmospheric boundary layers. So for the inflow turbulence generation, it can generally be categorized into 3 groups: precursor methods. So first you will run a preliminary simulation simulation, and you get the data downstream for the fully developed flow, and use the flow as an inflow condition for another simulation once you put the CFD or you put the building model in your computational domain. Or you can use a recycling method. So it has it consists of two domains. One is a driven domain, and once the flow passes through this terrain roughness elements, you can put a recycled plane downstream and collect data and use this recycled data as an inflow condition in your target domain. These two methods, they are relatively computational intensive because you have to run the CFD simulations or conduct the wind tunnel data to collect this spatial and the temporal time history data for the wind velocities. And compared to these two methods, synthetic method is relatively efficient and computationally efficient and easy to implement. So in the synthetic method, we have different categories, like we have a digital filtering method, we have a synthetic eddy method, and we also have random Fourier method. So currently the TInF, which is a SimCenter application to generate inflow turbulence, have incorporated these two digital filtering method and the synthetic method. You can choose the one inflow turbulence generation method using either the interface of TInF, or you can directly download the TInF codes in your local computer and compile it and use it like as your inflow function. So I will give a detailed introduction in the demo. So this is a quick introduction to the digital filtering method and the synthetic eddy method that have been implemented in our TInF application. So the basic principle for the digital filtering method is that they can model the spatial and temporal coherence on the data points that initially randomly generated in space and time through the digital filtering method. And the advantages of using the digital filtering method is that it can impose the spatial and the temporal correlation directly and can account for the inhomogeneous and anisotropic flow. And also they can reproduce the first and second order statistic and autocorrelation functions. And the disadvantages is that because it's generated through the digital filtering, so the physical constraint, like in the Navier-Stokes equations, the divergence-free constraint or the continuity equation cannot be satisfied. And to use the digital filtering method in the TInF, you can call this function turbulent DFM and set up the basic parameters by following the introduction in the TInF documentation. So the second method is the synthetic eddy method. It's based on the superposition of the representative coherent eddies. So the flow is assumed like to consist of the randomly generated the turbulent eddies with different size. So the turbulent eddies can be generated through the shape function in the synthetic eddy method, and the shape function is related to the coherence function in the space. And the advantages of using synthetic eddy method is that it's easy to implement the divergence-free constraint or the continuity equations in the Navier-Stokes equations, and also it can account for the inhomogeneous and anisotropic atmospheric boundary layer flows. And the disadvantages is that because of the limitation from the shape function in this method, it has difficulty in reproducing the arbitrary any prescribed turbulent eddies. And to use this synthetic eddy method, you can call the turbulent SEM inlet, or if you want to use a divergence-free synthetic eddy method, you can call the turbulent TF as SEM inlet in your open form the initial boundary conditions in order to use a TInF for inflow turbulence generation on the inlet surface. So today I will give two demos. First example is for the empty domain analysis. The empty domain analysis is important for the CFD simulations. So before you put a building model in your computational domain, you need to validate at the inflow condition, you set up your target inflow profiles, but when the flow travels downstream, there will be some distortion about your statistical properties of your inflow turbulence velocities because of the either assumptions of your turbulence modeling. You have the relatively large energy dissipation or generation, or you have some mesh problems for the truncation errors. So they have some issues in the distortion of inflow profiles. So you need to validate the inflow profiles downstream. It meets your targeted wind profiles, and then you can put the building model in your computational domain to run your CFD simulation. So today I will introduce how to customize your inflow conditions in the empty domain analysis using the wind tunnel data through the WEUQ application. So for this project, we collaborate with a NERF boundary layer wind tunnel at the University of Florida, and they provide the multiple inflow configurations and through changing the orientation and height of those terrain roughness elements in order to set up the different inflow boundary conditions with different friction velocity or roughness height. And the inflow velocities are collected at the end of the development section and before the building section model. And this data are used to validate our empty domain analysis. So to set up the inflow conditions in WEUQ, we use the TInF function direct specification. So we upload all the wind tunnel data collected from the wind tunnel experiments and to directly upload the files to the WEUQ to generate inflow turbulence profiles that characterize the specific atmospheric boundary layer flows. So the data we can obtain from the wind tunnel is mean velocity profiles and the turbulence intensity profiles at the streamwise vertical and span-wise directions. And to use a TInF to generate the inflow turbulence, we also need to know the parameters for the Reynolds stress and integral length scales. So those two quantities need to be calculated based on the data from the wind tunnel. So for the Reynolds stress tensor, we can obtain the values based on the turbulence intensity profiles. And for fully developed atmospheric boundary layer flows, the off-diagonal terms can be modeled by the friction velocity. And for homogeneous flows, other components are equal to 0. And for the integral length scales, we have some empirical formula that can be found in some the research publications, but users can also use other profiles to provide their integral length scales. So after the calculations are done, we can obtain all these parameters are needed in the TInF documentation, in the TInF application. So the first is the height of the building. So along the height, we need to provide the mean velocity profiles at each point. And the Reynolds stress tensor, we have 6 components, Reynolds stress tensor here. And you also need to upload the profiles at different height level, and also your length scales. We have 9 components for the integral length scales. So in this case, we have a baseline model for the empty domain analysis using the snappy hex mesh to generate the mesh in the computational domain. And we use large eddy simulations to model to generate the simulation results. And the mesh size is around 5 million. So I will show how to upload the wind tunnel data through the WEUQ. So this is Can you see my screen here for the WEUQ application? Okay. And this is an interface for WEUQ to use. So now we are introducing the digital wind tunnel feature, and this is a incoming feature that's going to be released by the end of the February. So if you subscribe the SimCenter newsletter, and will be going to be news once the new version of the WEUQ is released, and you can welcome to use the digital wind tunnel feature. It's a new feature in the WEUQ to run your CFD simulations. So once you go to the event module and you select the digital wind tunnel. Okay, and so here you can upload your wind tunnel data in order to generate inflow turbulence. So let's see. So once you store the data in SCV, in CSV format, and you can see those data like at different height levels have been uploaded here. So in the WEUQ applications, we will automatically generate the boundary data files based on the table users provide. So finally, the data will be stored in your OpenFOAM simulations in your constant directory boundary data, and you can see so this is at different height levels. It's corresponding to the table you provide, and also your mean velocity profiles. And after these files have been prepared, so the TInF function can be directly called and run the inflow turbulence generation based on the method you select. Here we use a digital filtering method to generate the time histories of the inflow turbulent velocities. And after this is done, and you can click Run at Design Safe. And you can specify the your job name and the number of nodes you want. Like in this case, we have 64. You can see here we need 64 processors to run the simulations. So in total, so let's specify we need the 2 number of nodes, and for each number of nodes we need 32 processors. So in total we have 64 processors, and you click the submit, and also you need to specify the maximum runtime. So far in the Frontera, they only allow the maximum time of 2 days, which is 48 hours to run the simulation. So after you click the submit the job, you can run the simulations, and once the simulation is done, like in 48 hours, you can click the get from the design safe, and you can directly download the data, like retrieve data from the guide from design safe. So this is how like we can upload the wind tunnel data to characterize the atmospheric boundary layer in the WEUQ. And so for the upcoming features, we will also provide the visualization tools that can plot, for example, the wind speed spectrum at the downstream at different locations, and to compare with target profiles. And also we will allow the tuning of the inflow parameters at the downstream to meet our targeted values that are provided by the wind tunnel experiments. So the second case is for the wind flow around building. So in the first example, we show how to upload the wind tunnel data directly to the WEUQ to generate inflow turbulence. So in the second example, I will show how to use embedded functions in the TInF to generate the time histories of inflow turbulence. So in this case, we don't have any wind tunnel data. So we need to select the functions like in the TInF to characterize the mean velocity profile, the Reynolds stress tensor, and the length scales. So in this case, we use a parallel function to characterize our inflow velocity, and also we use a parallel function to characterize our turbulence intensities. So the Reynolds stress tensor can be calculated based on the mean velocity profile and the turbulence intensity profiles. And for length scales, we assume the uniform distribution along the height. So there are two ways to specify like your inflow profiles following the parallel function. The first one is through the WEUQ interface. So if in the first case, we select the user-defined inflow boundary condition, but now we don't have any data, so we will select the inflow turbulence parameters. This is the second function to provide your inflow boundary conditions. So currently, we have three functions in the TInF. We have a uniform model, so the profile will be uniform along the height. We have an exponential model that follows the parallel the functions, and we also have a logarithmic model that follows log-law function to describe the atmospheric boundary layer flow for the mean velocity profiles and the turbulence intensity profiles. So if we choose exponential model, you can specify the magnitude. So the magnitude is the reference value in these equations. So for example, let's put it 10 here, and the reference angle is the angle between your local coordinate and your global coordinate. And you can find the detailed information in the TInF documentation. And the reference distance is your reference height in this parallel function. So if we make it like, for example, 0.5 meters, and alpha is exponential the value here. So normally for different terrain category, they have different values. So we can put 0.2 here, and you can also set up the profiles for your Reynolds stress, which is similar to the setup for the mean velocity, and also for the length scales. So this is the first method, like how you can use the interface to characterize your inflow conditions by using the embedded functions in the TInF. Another one is like you can download the TInF codes from the SimCenter GitHub and compile those TInF codes in your local computer, and you set up those flow parameters in your local laptop by using these different dictionaries in the OpenFOAM directory. And so to download the TInF codes, you can go to the SimCenter GitHub in the Turbulence Inflow tools, and they provide the two OpenFOAM versions, OpenFOAM version 6 and OpenFOAM version 7, to support the compiling of the TInF. And so if we download the OpenFOAM 7 Turbulent Inflow tools, so for example, so this has been downloaded to my local laptop, and so to compile the TInF codes, you need to open your terminal and launch your OpenFOAM applications, and then you go to your turbulent inflow directory, and so the all these different methods have been stored here. So DFM is for digital filtering method, and DFSEM is for the divergence-free synthetic eddy method we have introduced. And to compile this file, to compile the TInF codes, you need to I have compiled before, so I will do the wclean first, and then you just input the wmake command in the terminal, and they will compile all these functions for TInF. So after these functions are compiled in your local laptop, you can directly use the functions and call these functions in your local laptop. So to call these functions, you need to modify the 3 files. One is in the 0 directory for the initial and the boundary conditions. You need to modify the EU file to call the inflow turbulence generation method. For example, if you want to use a digital filtering method, you need to specify which type of function you want to use. And the second file we need to modify is that you need to add this new inflow properties dictionary file in your constant folder. And in this inflow properties files, this will specify the profiles for your mean velocities. We specified using the exponential function, and also specify your Reynolds stress profiles and give the reference values and the exponential values. And also for your length scales, you can specify those values in the inflow properties. And the third change is in the system directory and in the control dict that controls the runtime of your flow. You need to call these TInF functions. So the OpenFOAM will use this function to generate your inflow turbulence. So this is 2 examples like we showed today. One's using the direct specification in TInF using one tunnel database. Another example is to use the embedded function in the TInF to generate the inflow turbulence. And so if you have any questions, and you can either email me, and also you can send the questions through the SimCenter forum, and we'll quickly respond to your questions. And thank you. And I'm glad to take any questions if you have.
Great, thank you, Fei, for the presentation and working through those 2 examples. A lot of information you covered. There's a lot of details, a lot of fine details in all of the material you presented. So thank you for walking through it so clearly. We do have a couple of questions for you from the attendees. I'm going to start with one. Do you have to use WEUQ with OpenFOAM for the CFD simulation? Are you able to use other CFD solvers?
No, in WEUQ, the WEUQ is based on the OpenFOAM. So this is an open source CFD simulations. So if you want to use other like commercial software like Fluent or others, but like WEUQ cannot support that one.
Is it possible that it would be a feature or an option in the future?
Yeah, for non-commercial software or for the open source software, I think it's possible in the future. Like we include those softwares in WEUQ as it's an open source software. We can do the multiplications for the code part. But for commercial software, it's like a little bit difficult compared to the open source because we cannot modify any like embedded like codes in their softwares. So, but I think there is a promising. So if people like to use like Fluent or other commercial softwares, we can also include those features in the WEUQ to run the CFD simulations.
Good. And one other point of clarification is that WEUQ and all of the SimCenter software is open source and free to use. It runs at our partner DesignSafe, which is hosted at the Texas Advanced Computing Center at UT Austin. So an advantage of running WEUQ is that you are able to use the supercomputer there at TACC, and you use it free of charge, not because it's free, but because of the investment NSF has already made in supporting the Cyber Infrastructure Award for NERI, which is referred to as DesignSafe. So an advantage of running the open source software is you don't have to come to TACC with proprietary software and a license to work out with them. You get to use the open source versions free of charge. And the UQ component of WEUQ, Fei, can you describe what UQ capabilities or how they are, what they would be for a CFD simulation, if at all?
Yeah, currently for CFD simulations, we do not support the UQ because running one CFD simulation is very computationally intensive. So if you want to generate like 100 of like sampling points, so at each sampling point you run one CFD simulation. So that will be like a huge computational burden. So far we don't support the UQ in the CFD part, but for the WEUQ, like the UQ is for the you can see here, you still can generate the samples, and this is for the structural analysis. You can put the random variables for example, flow width and flow height, story height, and it will generate like 100 samples. And that will be like for each sample, they will run the OpenSea simulations to obtain the structural response. And totally it will collect like hundreds of sampling data to run your UQ analysis to calculate the structural response. And so to incorporate the UQ with CFD simulations are from the wind engineering, that will be like the incoming feature for our WEUQ, and we will like generate the samples like which characterize different atmospheric boundary layer inflow conditions, and will run multiple CFD simulations and collect the data to build our surrogate models to do the prediction. So that could be the incoming feature of the WEUQ, but currently the UQ is only incorporated into the structural analysis when using OpenSea to calculate the structural response under winds.
Okay. Regarding the turbulence length scale in WEUQ, is there a limit to the length scale? For example, is it feasible to do very large scales, like something more than 10 times, I guess, the height of the structure?
Is it mean the integral length scales that are specified in the inflow boundary condition?
Yes.
Okay. Let me see. So, like this one. So, so far we use integral length scales that are like so for the first example, the data obtained from the wind tunnel test, and so if you have like CFD guidelines, we'll use those recommended values for CFD simulations. But if you really have very large integral length scales, so theoretically it's feasible to run the CFD simulations, but you need to consider about your computational time if you do have a very large length scales, and also the numerical accuracy after you run the CFD simulations. So I will recommend you just following the CFD guidelines when you specify the integral length scales for CFD simulations.
Okay. For as a complete novice to wind engineering, what are the wind velocities that it would be simulated? What is the range of wind velocities that might be run in a CFD simulation? Are they on the order of like hurricane type wind speeds? Are they under much lower wind speeds? Can you explain a little bit for somebody who doesn't have the background? that you do?
I see. I think CFD simulations can simulate both for the low speed wind and also high speed wind. Like if you have a hurricane, you have a tornado, CFD simulation also have the capabilities to model such the wind hazard simulation flows. And today we talk about the two cases. These are for like in the natural wind and the buildings to simulate the wind flow around the building. But if you do have very like a large magnitude of wind velocities when you're simulating the buildings and you want to save some computational cost, probably you can also impose some like velocity scales similar to the wind tunnel and to model the CFD simulations, like to save some computational cost.
Okay. Another question, not another question, but a question about the HPC platform at TACC. Is it free to use? How much computational resources are available, and how do we obtain them? Is that something you feel comfortable answering? Okay,
yeah, I think like so if you submit the job through the WEUQ interface, like you have a free access to the Frontera HPC nodes. But if you want to directly submit the job through your terminal, I think you need probably apply for a research proposal to the TACC, and they will allocate some computing nodes to you, and you can use your own nodes to run the simulations. So that's what I know about the simulations using HPC resource in TACC.
Correct. So through the NERI program, NERI is the Natural Hazards Engineering Research Infrastructure. It's a program funded by the National Science Foundation. It funds the SimCenter and it funds DesignSafe. And at DesignSafe, they provide resources, computational resources for you to run jobs in natural hazards research. So you're able to run a certain amount of allocation free of charge. If you go over that directly through your account at DesignSafe, you might be able to apply for additional resources. If you run the WEUQ application or any of the other SimCenter applications, you are actually going to be running on our account, and you will not be charged on your own account. So the limitation will be the runtime and how long you end up waiting in the queue based on the number of nodes requested. So there is a computational limit, which is the runtime, essentially. Okay, and one other question about UQ. Is it possible to perform UQ with ABL simulation presented today? So I think we answered already that that the UQ component is in the structural model. Right. So would you ever run one of these with UQ or?
Yeah. We are also implementing like this new feature, like to incorporate the UQ in quantifying the different atmospheric boundary layer flows. So we'll like change the inflow parameters based on different like a characteristic of the atmospheric boundary layer flows, and later we'll integrate with QualFAM for the uncertainty quantification of the inflow conditions. So that could be the incoming feature probably in 1 or 2 months. So yeah, okay. But so far the UQ is only incorporated into the structural analysis.
Okay, I think that two things. One, I want to thank the attendees for your questions. These were really, really helpful. I want to remind you that additional questions or very specific questions for Fei or the other developers of the SimCenter applications, the resource here that she's pointing to is the SimCenter forum, and we invite you to submit your questions as well as your feature requests here at the forum. I also want to point out that you're welcome to join other live expert tips brought to you by the NERI SimCenter. You can go to our webpage, which is simcenter.designsafe-ci.org, and find other upcoming events. You can register for the SimCenter newsletter and join other events such as this one. So I want to thank Fei for her presentation and for answering our questions today. And this concludes today's live expert tips with the NERI SimCenter. We hope you've been inspired to pick up the examples that Fei presented and perhaps adapt them into your own research. So thank you very much, Fei.
Thank you all for attending the live expertise, and thank you, Matt.